by the planet on which it is present. We call it as weight. Gravitational force exerted on a body by the planet on which the body is situated. You call it as weight. So a body which is on Earth will have weight due to Earth's gravitational force. A body which is on Moon will have weight due to Moon's gravitational force. A body which is on Jupiter will have weight due to Jupiter's gravitational force. So as gravitational force due to each planet will be different, which depends on the dimensions of the planet, the gravitational force will also be different. If gravitational force is different, weight will also be different. So weight of a body changes from planet to planet or place to place in space. But mass does not change. It is constant, it is fixed for a given body. Mass, because it is the quantity of matter contained in a body, it is constant. Mass is measured in kg, weight is measured in Newton. Mass is scalar, weight is vector. Okay. So if you have a body of mass m, then its weight will be mg. Simple. If you have body of mass m, its weight will be m into g. Multiply mass by acceleration due to gravity, you will get the weight. And acceleration due to gravity, each planet has its own value. For Earth, it is 9.8. For Moon, it is 9.8 by 6. For Mars, it is something else. For Jupiter, it is something else. Okay. So keep this point. If you are given mass and you want to weight, simply multiply mass by acceleration due to gravity. You will get weight. W is equal to mg. Important. Right. Next, second one was, I was telling you about normal reaction. Normal reaction. So we have to continue from here. Yes. So second force, normal reaction. If you remember, if you place a body on a surface, let us say this is the table, and on the table you are placing a body of mass m. Okay, if mass of this body is m, then there will be its weight, which is mg, and the direction of weight will always be vertically downward. I told you, weight of a body always acts vertically downward. So mg is acting vertically downward. Mg, weight is a force. Okay, if force acts on a body, the body should get accelerated according to second law, F equal to ma. But this body is not getting accelerated. It is at rest. Then this can happen only when the weight of the body is balanced by some other force. Weight of the body is balanced by some other force. Basic point, only a force can balance another force. Force cannot be balanced by velocity, force cannot be balanced by acceleration, force cannot be balanced by energy. Force can be balanced only by another force. So if this body is at rest in spite of its weight mg acting downward, that means some other force must be acting on the body in the exactly opposite direction to weight, and we call this force as normal reaction, N. Normal reaction. Why is it named so? Because it is a reaction force. You will get this normal reaction only when weight of this body acts on the table. Weight on the table is action, and table applying force on the body is reaction. That's why we have reaction in its name. Then normal. Normal means here not your normal of English, it is normal of mathematics. Normal of mathematics means perpendicular. So this force, the direction of this force will always be perpendicular to the surface with which the body is in contact. That's why it is named as normal reaction. It is a reaction force which always acts perpendicular to the surface with which the body is in contact. Okay. Now imagine you suddenly pull away this table. All of a sudden, very quickly, you pull away this table. Then what will happen to this block? Will it stay there in air? No, it will fall down. Why is it falling down? Because of its weight. Where is the normal reaction gone? There will no more be normal reaction, because normal reaction acts on a body only when there is contact. As you pulled away the table, the block is no more in contact with the table surface. So no contact means no normal reaction. No normal reaction means weight is not balanced, mg. Weight is not balanced means there is only one force which is pulling it down. So the block falls down. But as long as the block is in contact with the table surface, there is normal reaction which is balancing the weight. So the block will be at rest. This is normal reaction. Okay, so it is a reaction force that acts on a body due to contact with a surface or another body. This is normal reaction. And the nature, characteristics of this normal reaction is normal reaction. It always acts perpendicular to the surface with which the body is in contact. Always perpendicular. And note this point. Then it is a contact force. You'll get normal reaction only when there is contact between bodies. Without contact, you don't get any normal reaction. Okay. Then, if you take some examples, simple example, this is a surface. This is a body of mass m. Its weight is mg. Its normal reaction on this is n. How much is n? N is equal to mg here, because the body is at rest. Okay. Suppose you have a situation like this. This is the incline of angle theta. On this incline, we are placing a body of mass m like this. And this body is stationary. It is not sliding down. It is stationary. So if it is stationary, how is there normal reaction on the body? Slope incline is the surface now. Body is on the incline. Is there a normal reaction? Yes, there is normal reaction, because wherever there is contact, there will be normal reaction. There is contact here, so there will be normal reaction. In which direction? Like this. Will normal reaction be like this?
So perpendicular.
This is wrong. Normal reaction will not be like this. Normal reaction always acts perpendicular to the surface. Perpendicular to the surface, not to the body. Perpendicular to the surface. Incline is the surface. So perpendicular to the incline means this. This is the direction of normal reaction. Okay. And if you take weight of the body, how much is its weight? Mass is m, so weight is mg. And what is the direction of weight? Will it be acting like this? mg.
No, sir. Exactly downwards.
Weight always acts vertically downward. This is the direction of weight, mg. Okay. Then if you recall your vectors, you can resolve weight in, I can resolve weight into two components. One component along the incline and another component perpendicular to the incline. From geometry, if this angle is theta, we have this angle also as theta. And I think I told you, I stressed upon this point to remember this particular situation. You are going to get many situations like this. If you remember, while discussing vectors or components of a vector, I gave this example. Now we are using it here. So weight is acting vertically downward mg. One component of weight is along the incline, parallel to incline. Another component is perpendicular to the incline. From geometry, if this angle is theta, we'll get this angle as theta. If this is theta, what will be this component? mg cos theta. What will be this component? mg sin theta. Now here, how much is normal reaction? Here normal reaction is equal to mg cos theta. Because if you look in perpendicular direction to the incline, in this direction, you will see that n and mg cos theta are balancing each other. N cannot be balanced by mg because n is like this, mg is like this. These two cannot balance each other. They are not in opposite direction. mg cos theta is this. So this can balance this. Therefore, n is equal to mg cos theta here, not mg. If the body is on horizontal surface, in this example, n is mg. On an incline, n is mg cos theta. Suppose we have a situation like this. This is, let us say we have a what is it, two planes like this, a V-shaped container something. And in this, we have, I'm placing a sphere or a ball.
Sir,
Yes,
sir, how did you name them the arrows as mg cos theta, mg sin theta, sir?
they are components of mg. This is a sphere of mass m, which is placed in a groove like this or a container like this, V shape. Then, how much is its weight? mg. In which direction is it acting? Vertically downward. So weight is acting vertically downward. mg. Okay. Is there normal reaction? Is there normal reaction? There is normal reaction. Wherever there is contact, there will be normal reaction. Where is the contact? Contact is here at this point. So you'll get normal reaction here. Due to what? Due to this surface.
Reaction, sir.
Huh?
We get two normal reaction
Two
forces.
normal reactions. Yes. So this is the point of contact. So one normal reaction is this in this direction. I will call it as N1, perpendicular to the surface. And here also there is contact. So here you'll get one more normal reaction. Let us say N2. Two normal reactions are acting on the sphere. And if you just apply your knowledge of vectors, this is N2, this is N1. The resultant of these two will be something like this, parallelogram.
Diagonal, sir.
So N1 and the resultant of N1 and N2 will be this, let us say, which is some NR. And this NR, resultant of these two normal reactions, it is balancing the weight. That's why the ball is stationary. Resultant of N1 and N2 is balancing the weight. N1 cannot balance weight. See here, N1, which is acting in this direction, cannot balance weight, which is acting in this direction. and at the same time N2 which is acting in this direction cannot balance weight which is acting in this direction. But if you combine N1 and N2, the resultant will be this, which will be exactly opposite to the weight. That's why weight is balanced by N and the ball is stationary. Next. Next is suppose you have, this is a horizontal surface, this is a vertical wall, this is a horizontal, say, floor, and a rod is placed like this, rod or ladder, something is placed like this. Then is there normal reaction on the rod due to the
Yes.
walls or floor? Yes, there is normal reaction. Where is it? It is here. This is here, there is contact. So normal reaction will be there. Let us say this is N1. Again, here there is contact. So there will be normal reaction like this. Say some N2. So this is normal reaction. Where do you get it? Wherever there is contact between bodies, you will get normal reaction. Wherever there is contact, there will be normal reaction. Okay. Second force. Third force. First was weight. Second is normal reaction. Third is, let us take tension. Tension. Tension, not your what you call psychological tension, because some people feel they get tensed for small
Tension
stuff. It's
and
not like
strings, sir.
that tension. This tension is a force which appears in strings to which load is applied. Suppose, very simple um, situation, simple example. Suppose I have a block of mass M and I am suspending that block by using a string, a thread, a wire, a rope, something. A block of mass M is suspended vertically by using a string. This is the string. And the strings that we consider here to understand tension, these strings are massless and inextensible strings. Massless and inextensible. Massless means the mass of the string when compared to mass of the body which is suspended to it will be very, very less. Like say the mass of this block is some 1 kg and mass of this string is some 5 gram, which is negligible. So we ignore the mass of the string here, and also we treat the string to be inextensible. Inextensible. That means it does not stretch like a rubber band. If it stretches, situation will be different. At different points, you'll get different values of tension, which is a advanced thing. You don't get to study that here. We'll treat the string to be it does not stretch. If you apply any load to the string, it does not stretch. That's what we call as inextensible. So if you have such a massless and inextensible string to which a load is applied when some body is connected to it, so that string is bearing the weight of that body. What happens? What is happening here? Now, if you just look at it generally, nothing is happening. A block is suspended by a string. What will happen? It will be hanging in air like that. But if you look at it carefully, the point that you should observe is if this block of mass M is there, it is hanging in air, that means its weight will be there. How much? mg. In which direction? Vertically downward direction. mg weight is acting. Its weight mg is acting vertically downward. Okay. What does Newton's second law say? F equal to ma. Wherever there is a force, there must be acceleration. Here there is force mg, but there is no acceleration. The block is not getting accelerated. It is not falling down. Why? What is happening? Because it is fixed. It is tied to a string. Suppose if I cut this string, this block suddenly, immediately it falls down due to gravity. Okay, that means as long as the block is tied to this string, what is happening? It is balancing the weight of the block. Who is balancing? String is balancing. Because if you cut the string, the block falls down. That means string is doing something. This string is doing something to balance the weight of the block. What can a string do? Who can balance weight? Weight is a force. Only another force can balance a force. That means this string is applying some force on this block, due to which it is balancing the weight. You call this force as tension force, or simply tension. The force developed in strings whenever load is attached to them is called tension. Okay. Now, how do string produce this tension force? What happens actually inside? If you, let us say you are having a very powerful microscope, and in that microscope you are looking at this string, then that string will look something like this to you. This is the block of mass m, and what are these? These are atoms or molecules which make up that string. Okay, and you know there will be bonding between neighboring atoms or neighboring molecules. Let us say this is molecule 1, this is 2, this is 3, this is 4, this is 5. When there is no load applied, these molecules will be at a certain equilibrium separation because of their bondings. Let us say they are molecule 1 and molecule 2. They are separated by some 1 millimeter, just to understand. Okay, 1 millimeter. And there is a force between 1 and 2. What force? Bonding, molecular bonding. Molecular bonding is present between 1 and 2, between 2 and 3, between 3 and 4, 4 and 5. Okay. Now, if I attach a load here, what is happening? This load is trying to pull molecule 1 downward, and molecule 2 does not allow that to happen. If molecule 1 tries to go away from molecule 2, molecule 2 will pull it towards it. Okay. And if 2 tries to go away from 3, 3 tries to pull it. And if 3 tries to go away from 2, 2 tries to pull it down. 4 tries to go away, 3 tries to pull it. And 3 tries to go away, 4 tries to pull it. So there are, like, suppose you are standing in a line. Some 5 students are standing in a row, holding their hands like this. And the condition is they should not let go their hands off. Suppose if I pull the last fellow towards left, then what happens? This is 1, 2, 3, 4, 5. If I pull the last fellow towards left, this fellow number 2 pulls 1 towards him. Okay. And if 2 tries to go away, 3 tries to pull 2 towards him. And if 3 tries to, let us say, I'm applying a force on 1 towards left and another force on right, on 5 towards right. So 5 is trying to go towards right, 4 tries to pull it. At the same time, 4 is trying to go towards left, 5 tries to pull it. Like this, there will be pairs of molecular forces acting between the individual molecules. And the overall resultant of all these forces that we see, that's what we are naming it as tension developed in the string. So you'll get tension in a string only when it is loaded. If you just move this mass, if this mass is not there, there is no tension in the string. Only when there is load applied to a string, you'll get tension in it. This is tension force. What are the characteristics? So what is its origin? Its origin is molecular. Its origin is at molecular level. What can we say about it? It is due to molecular attraction. Then it always, what is the direction of tension? It always acts along the length of the string. It always acts along the length of the string. Because suppose if a string is like this is a string, or take this string to which mass is suspended. Tension in this string can act either in this direction or in this direction, but cannot act in this direction. Because in this direction there is no string. If there is no string, how can tension act? Tension will not act in this direction, tension will not act in this direction. Tension will act only along the length of the string. Okay. And what is its direction? Direction of tension, it has two directions. Tension acts in both directions. At a given point. At a given point. What does this mean? Take the same example. Mass m is attached, its weight mg is acting down, and tension is produced in the string. Suppose I take a point, this point on the string, then tension will be acting above this point in this direction and below this point in this direction. This is tension, this is also tension. Why? Because of this thing which I told you. If you take molecule 3, 4 is pulling molecule 3 upward, 2 is pulling molecule 3 downward. So with respect to this molecule number 3, tension is acting upward above it and downward below it. Similarly, if I take this point as reference, some point P as reference, then the molecule which is at present at point P is being pulled up by the molecules above it, and at the same time it is being pulled down by the molecules below it. So tension has two directions, upward and downward. Which direction should we take? Which direction should we take? We should take that direction of tension which is opposite to the body of interest. So the body of interest. Body of interest means the motion of the body which you are interested to study in. In this situation, I am interested in studying the motion of this block, which is suspended. So the direction of tension that I should take here will be opposite or away from that body. Away from that body. Need not always opposite. It is away from that body, which is this. So which is the direction of tension acting on block of mass m suspended by a string like this. Okay. Suppose I'm interested in studying the motion or the status of this ceiling from which the block is suspended, this thing. Then on this ceiling, The direction of tension is downward, away from the body. If your body of interest is the ceiling, then tension is downward. If your body of interest is the block, then tension is upward. I'll write that point here. Direction of tension is always away from the body of interest. Okay, then also an ideal string is massless and inextensible. Massless and inextensible. This is about tension. Yeah. Next, tension. Next one, next force is friction. Friction. You might have heard this term friction somewhere, or you might have experienced. We experience it almost in every work that we do. If you are writing, it is because of friction. If you are able to walk safely on ground, it is because of friction. If you are able to apply brakes to vehicles and stop them, it is because of friction. If vehicles are able to move on the road, it is because of friction. If you are able to drive nails in the walls, it is because of friction. If you are able to hold anything, it is because of friction. Friction is present everywhere. Okay. To understand what is friction, let us say this is a horizontal surface, and on this horizontal surface, I am placing a body of mass m. Okay. Body of mass m. If I leave it as it is, it will be at rest. It will be at rest. Suppose I apply a small force on this block. Small force. How much? Let us say, for example, 1 Newton force. Then I see that this block does not move. For example, you take a table or chair, something on a horizontal floor, and you try to apply a small force on it with your finger, index finger, very small force. The table does not move, right? The table does not move. But what does the second law say? F equal to ma. If there is force, there must be acceleration. If there is force, there must be acceleration. Of course, the force that you are applying is very small, but for very small force, there must be very small acceleration at least. That means the table should move very, very slowly at least, but it does not happen. It will completely at rest. If you further slightly increase the applied force, still the table is at rest. Apply increase further, still the table is at rest. Like this, up to a given like up to a particular value of force. Like say I am applying 1 Newton, I am making it 2 Newton, 3 Newton, 4 Newton, 5 Newton. Like this, up to 10 Newton, I see that the table does not move. Then, if I slightly increase the force beyond 10 Newton, if I make it 11 Newton, I see that the table starts to slide. Okay, this is fine. But what about 1 Newton to 10 Newton force? Where did this force go? Where did this force go? This force cannot go anywhere. It must be balanced. It must be balanced. 1 Newton, 2 Newton, 3 Newton force, all these forces that you applied and the table did not know, these forces were balanced by some other force. Balanced by some other force. What is that some other force? Can it be weight, which acts like this? No. A force which is in this direction cannot balance a force which is in this direction. Common sense. Okay. Or is it the normal reaction? No, because normal reaction is upward. Applied force is towards right. These two forces cannot balance each other. So that balancing force is neither normal reaction nor weight. Then what is it? It is some other force which we call as friction, which is acting between the surface and this body. Friction force. So friction is a force which opposes. Friction is a force which opposes, not motion, which opposes the relative motion between two bodies. Relative motion between two bodies. Remember this word, relative motion. Many students have a wrong understanding that friction always opposes motion. It is not so, not always. In some situations, it might oppose motion, but not in all situations. But in all situations, it opposes the relative motion between two bodies. What is the difference between motion and relative motion? We'll discuss that when we study friction in detail. Okay. What are the characteristics of this friction? The direction of it is a contact force. It is a contact force. You'll get friction only when there is contact between bodies. Okay. Then its direction is always opposite to the direction of intention of motion of the body. Direction of intention of motion. Remember this word also. Don't remember the direction of friction like always opposite to the motion of body. Not always. It is always opposite to the direction of intention of motion of the body. Okay. Then practically the magnitude of friction is found to be directly proportional to normal reaction. Friction is directly proportional to normal reaction. And how much is the friction? Friction is equal to mu n. What is mu here? Mu is called coefficient of friction. What is n here? Normal reaction. This is only magnitude. Don't think that friction is equal to normal reaction. It's not. That direction of friction is this. Direction of normal reaction is this. The directions are different, but their magnitudes, they depend on each other. Greater the normal reaction, greater the friction.
Sir,
Hmm.
Sir, why did you write direction of intention of motion, sir? Directly we can write it as direction of motion. No, sir.
No, it's not always opposite to direction of motion of the body. In some situations, not in some situations, in all situations, the direction of friction will be always opposite to the direction in which the body wants to move. How is that? We'll study that in detail when we go into details of friction. Friction is actually friction parts forms half of this chapter, laws of motion. 50% of this chapter is related to friction. So it is to be studied in detail. For now, I am just giving you the idea of what is friction. Okay, this is friction. And there, the other details are there. We'll get into them when we go into the details of this topic. One last force is left out, which is spring force, fifth one. Spring force. As the name itself says, you uh, find this force in springs. Springs, you might have seen springs. You have springs in your pens. So if you take a spring and stretch it or compress it, it again tries to come back to its natural original position. There is a force which is developed in the spring when you disturb it. We call that force as spring force. How much is that? On what factors does it depend? You have to study that in detail. We'll do that in our next class tomorrow. Okay. So we'll continue tomorrow. See you and good night.
Thank you, sir. Bye, sir. Good night, sir. Thank you, sir. Bye, sir. Good night, sir.
Sir.